Hello everyone, my name is Abdurrahman Basalan and today I'm presenting the ECE792 Linear Systems course project, and the main article of the project is Neural Network Adaptive State Feedback Control of a Magnetic Levitation System. This article is published in the 26th Chinese Control and Decision Conference in June 2014, and it is available online by IEEE Explore web page. The location of conference is Changsha, China. And here you can see the contents that I will talk about today with these titles. So let's go to the statement of problem. The statement of problem: magnetic levitation system is a new mechatronic technology which can make an object levitate without contact and then decrease the mechanical loss. Magnetic levitation is typical technologies which are combined with electromagnetism, dynamics, power electronics, and automation, and developed with these technologies and theory. Magnetic levitation system is mainly composed of a high-intensity rare earth disk, an electromagnetic drive coil which produces a magnetic field in response to a DC current, a laser sensor which measures the magnetic position using the reflective properties of the disk surface, a glass guide rod, and the metal bracket as shown in figure 1. The motivation of this paper is in nowadays more and more domestic and foreign scholars have devoted themselves to the study of magnetic levitation technology. Magnetic levitation system is complex system which are nonlinear, unstable, and uncertain. These characteristics adds the difficulty of designing the magnetic levitation system controller. The feedback control is simple structure, good adaptability, and great robustness. However, the state feedback control is based on the precise mathematical model. So that means state feedback control is not adaptive enough in nonlinear and uncertain control systems. And it is not sufficient for control whole system with uncertain inputs, that we can say. So, when we talk about the modeling of a magnetic levitation system, a magnet disk is levitated along a glass guide rod by a repulsive force and an attractive force produced by the coil. The authors consider a mathematical model of the magnetic levitation system. Magnet disk is acted on by forces from the drive coil, from gravity, and from friction in figure number 2 that you can see. So the Y refers to the position of magnet disk from the coil, and the equation of motion for the magnet is, you can see here is the equation where m is a mass, refers to mass of the magnet disk, c is a friction constant, g is the gravitational constant, and fu is a repulsive force for the magnet disk produced by the coil, and you can see the equation here also, and where u is control input voltage applied to power amplifier for the coil. A and B are some constants determined by numerical modeling of the magnetic configuration. So the radial basis function network is, you can see the structure of the RBFNN in figure number 3. X is the input vector. The radial vector of RBF network is metric H, which is the Gaussian function it includes. And so we have the when the inputs are matching with the matrix H, we are getting our output. And so the Gaussian function has also matrix C and matrix B. Matrix C is the being the center of the receptive field, and matrix B is the width of the Gaussian function that we have. And so the Gaussian function of RBF network is modeled like this. So x is our input, Cj is the width of the Gaussian function, and this equation comes from the matrix B. And so we have also the weight vector as matrix W, and the RBFNN output is going to multiplication of weight vector and the radial vector of RBF network. And we are adding all these inputs at the same time. And the performance index function is defined as with these equations. So we have also the Jacobian matrix, which includes the center of the receptive field and the input and the width of the Gaussian function also. And in figure number 4, uh, you can see nonlinear plant is referred to magnetic levitation system. U is our input, Y is the output of magnetic levitation system, and this output is going into the RBF network again, and there is the other processing happening inside this plant. So the identification simulation, we can say the the left side figure is the output of nonlinear plant. I'm sorry, the input of the nonlinear plant, and the right side figure is the output of nonlinear plant that we have. Authors are used 3 neurons of the input layer and 5 neurons of the hidden layer. The learning error of RBF NN is in figure 7, which is the below side. Uh, the authors, the approximation ability of the network is very good. They identified, and the identification error is almost zero and achieve a good identification result. So the design of a neural network adaptive state feedback controller, which we have, like this article proposes the neural network adaptive state feedback control scheme based on RBF neural network. Firstly, a state feedback controller is designed, and then to improve the system performance is combined with PI controllers. The system input is U equal to U1 plus U2, and the PI controller has also output with U1. And we have the real output, which is the state feedback controller, and the U2 is uh, U2, you can see the output of the state feedback we have, and where K1 and K2 are the feedback. K1 and K2 are state feedback parameters of the state feedback controller. X1 and X2 are the states of the plant. And the error and the system average square error, as you can see from the output that we have. The simulation results, they have like some constant number, such as the mass of the magnetic levitation system and some other constants, learning parameters, the initial conditions that they have. The PID controller simulation results in figure number 9, and neural network adaptive state feedback controller simulation results in figure 10. As a conclusion, so the radial basis function neural network is implemented into magnetic levitation system. Neural network adaptive state feedback controller is designed. System has better adaptability and stability compared with conventional PID controller. So for next studies and researchers, according to me, the other artificial neural network types can apply and observe the results in terms of error rate and output stability. Thank you so much for listening to me. If you have any questions, you can let me know through my email address. Thank you so much.